Hello students, welcome back. We went through a couple of examples already. Well, to tell the truth, we went through one non-trivial example. The previous example with sine and cosine, that wasn't really an example. This was a real example. Let's go one more here. Okay, hopefully this one's a little bit simpler. Let's see. Previously we had the derivative and second derivative. But here I only have the second derivative, so hopefully this is a little bit simpler. But in any case, let's begin with the interval of convergence first. So interval of convergence, we have to find out the singularity first. Here we go. Divide by the leading coefficient, and we have denominators, so singularity is 1. And we are dividing, we are expanding from t equal to 0. So the distance from the center point 0 and the singularity 1 is 1. So the radius of convergence is 1. So consequently we have that. We have this interval of convergence. Okay, all right. Now get the power series expansion of the original function, derivative function, and the second derivative function as usual. Original, green. Derivative blue and second derivative red as usual. And then here's my function, right? Here's my equation. There's some space in between. And then this is red and this is green. And no blue because there's no first derivative term. So green series. After substituting it, this is what we get. Okay, and then we'll have to break up this parenthesis here. So distribute this series times 1 times t. Oh, I skipped a step. Okay, all right. Let's not skip a step. Okay, distribute around, and this is what we get. Times 1, and this is for times t. And then this times t part, that one, I can multiply this t to this n minus second power to get n minus first power. That'll result in the final expression there. Is everybody comfortable with all these computations here? Original, first derivative, second derivative, the usual deal. Power series, term by term derivative, and then another derivative. Original ODE, and plug those in. And then distribute. And then taking this t inside, we get that. All right. We have nth power here, n minus first power here, n minus second power here. Looks like some index shifting is order. And we need 2 index shifting. We want one for this and one for that. Make sense? So 2 index shifting are required. Okay, let's go. This one blue, this one red. Okay. From here, let's see. From here, for red, we're doing n as n plus 2. We're taking this substitution. And we take this substitution for blue. All right, so n plus 1 minus 1, so t to the nth power, okay. And then we have n plus 1 here. And here this became n plus 1. and then n plus 1 minus 1, so we have n like that. Same goes for red. Okay, some more manipulation to go. I'll have to start from the same starting point, and that's not going to be too much of a problem. I can always make it starting from 0, because when n equals to 0, this thing is 0, right? So adding 0, that's not going to make any difference. And this is typically the case for ordinary points. You don't have to worry too much about the starting points. Now, if you apply the power series method at singular points, then that could be a problem. And that's something we are going to discuss in the next lesson, next week. At this moment, let's just keep to just ordinary points, so you don't really have to worry about this kind of thing. Always make everything starting from n equals to 0, no problem there. And then take the like terms together. T to the nth power is a like term, so we get all these. Is everybody with me here? In case you aren't, let's have a recap. As for interval convergence, it's actually a separate deal. Make it into the standard form and see if you have any singularity. We have denominator, so yeah, we have singularity. Denominator hits 0 when t equals to 1. And the distance from the center point 0, and the singularity is 1. So that's the radius of convergence. Consequently, we get this interval of convergence there. Okay, and then we have the usual power series expansion. Original power series, the derivative term by term, and the second derivative term by term. Original equation, and the plug in the derivative, the second derivative, red, and the original, green. Break out the parentheses. Oh no, this is just substitution. And then here, break out the parentheses. And then times constant, no problem there, times t expression, and then we have change in the power. So we have that. All right, and then we apply index shifting. So rewrite this one like that with color coding, and then apply index shifting to red series and blue series separately. For red series, we are replacing n by n plus 2. So blue series, n by n plus 1. So n by n plus 2 and n by n plus 1, that's for blue. So red, we do this, and for blue, we do this. The detail is left to the students. Okay, so we did the index shifting, probably the hardest part. And then make everything starting from 0. Actually, there's no big deal. That always holds. For ordinary points, no problem there. Index shifting is hard. This is not difficult. So okay, we got everything. T to the nth power, all done. So take the like terms together. We have this b coefficient part, and that has to be 0. And that gives me the recursive equation there. Here. Solving for Cn plus 2, flip these to the other side and divide by this n plus 1 times n plus 2. This is what we get. All right. And then you can find out the general solution using starting from C0 and C1. So n equal to 0, you're going to get C0 and C1 will give me C2. And then C1 and C2 will give me C3, and so on. Here we go. When n equals to 0, we're going to get C1 and C0 will give me C2. And here's a computation. Just tedious numerical computation, you see. When n equals to 2, C2 and C1 will give me C3. A little bit of numerical computation. In the end, we get something like this. something is not right. This C0, yeah, not there. Oh, it's already there, so okay, this is right. And then plug in n equals to 2. C4 is determined by C3 and C2. And some further simplification, we get that. And then you just stop there. Do you see a pattern? Maybe you can, but never mind about the pattern. For several terms, and then you can just leave it at that. And then here's a general solution. You see, general solution is like this. And then here's the recursive relationship, where C0 and C1 are arbitrary. And first several terms you can calculate like this. And then for computers, you can calculate first 100,000 terms in a matter of millisecond. But if you don't do these computations and just go directly to this, skip these computations, going from here to there directly. And if that's a 10-point problem, maybe I give you 1 point off and give 9 out of 10. Maybe just 10 out of 10. It's not going to be too much of a deal. This computation here is just tedious computation. That should not be causing too much of headache, you see. You have to put appropriate effort in smart way to the important steps. And this kind of computation of first several terms is not an important step. There are many important steps here. Interval of convergence, okay, that's an important step. Simple, but it's important. Putting the power series putting all those power series in, and then breaking off the parentheses to get the get this kind of expression, that's important. Index shifting is extremely important. And then in the end, getting the recursive relation, so setting the inside equal to 0 to get an recursive equation, that's extremely important. And then you just move into the final answer. And the computation, numerical computation for first 2 or 3 terms, I don't care too much about it, to tell the truth, but there's no question it is better to have those kind of things there. Maybe about 2 terms, 3 terms, that's about it. Here I use my mathematical program to calculate many. Of the 10, I can do up to 20 really easy. Okay, all right. I don't know whether these kind of expressions make sense or not. Let's go back to about 10. In the end, we have this kind of solution. Okay, so much for the power series method for ordinary points. In the next lesson, we are going to consider power series method at singular points, and that's going to cause a bit of difficulty. And one of the most prominent difficulties right here. For ordinary points, just going from n equals to 1 to n equals to 0, that made no difference. Because if I just start from n equals to 0 there, this is 0, so you're just adding 0, so this series makes no difference. But for a singular point, it's gonna matter. Okay, so much for PowerPoint method. Set 1. Let's meet again in lesson 12, power series method, set 2.